Welcome to Spring LIB.
Okay, here we have a manufacturer wanting to make a rectangular box with no top, and the volume is 10 meters cubed. We're told that the material for the base costs $10 per meter squared, and the sides, material for the sides costs $6 per meter squared. And we're given a little bit of dimension. We are told that given a certain width, then the length of the box needs to be twice that width. And we're not given specific information on the height, but we can figure it out based on the fact that the total volume has to be 10 meters cubed. So let's take a look at that first. And then our main goal is to find what are the dimensions to save money, right? To get the minimum cost. So let's go ahead and work on the left here regarding the volume. We know volume of a rectangle is length times width times height. And we are told that the length is twice the width. We don't know the height, but we do know that the volume is 10 meters cubed. So if I solve for h then would be 10 divided by all this, and that would be divided by 2w squared. And I can reduce dividing top and bottom by 2, so 5 over w squared. So now I know that the height is 5 over w squared. All right, awesome. Okay, so next, let's go ahead. Let's create an equation for cost, and then we can take the derivative and work towards minimizing the cost. All right, let's do that. Okay, so we're going to create a function of cost that is a function of w. And basically, the cost is $10 times the area of the base. Well, it's $10 per meter squared times the area of the base, plus $6 per meter squared times the area of the sides. Okay, so let's go ahead and find the area of the base in terms of W. And I'm going to leave out the units for now to keep it simple for solving. And at the end, we'll make sure our answer is in correct units. Okay, so we have 10 times the area of the base. The area of the base is just the length times the width. So 2w times w. Then we have $6 per meter squared times the sides. Well, we have two sides that are like this. So we're going to have twice height times the width, but the height is 5 over w squared times the width. And then we have two that are this dimension. So we have plus, actually I can fit it all in the same parentheses. Let's do it like this. Okay, plus 2 of those sides. Those sides are made up of 2w times the height, and the height is 5 over w squared. All right, so let's clean this up because we want to take the derivative, and we might as well do it when it's cleaner and not messy. Okay, so this first term is 20w squared. And let's see, if I look inside the parenthesis on the right, one of the w's cancels for each part. Then it looks like I have, this is 10 plus 20. So that makes 30, and 30 times 6 is 180. So I get plus 180, and we still have that w on the bottom. All right, let's go ahead and get a common denominator. I'm going to multiply this part by w over w. That will give me 20w cubed plus 180 over w. And actually, I want to take the derivative first. So even though this is true, we are not going to do that yet because I want to take the derivative, and I can probably more easily take the derivative when it's not that big fraction. So let's just do derivative now. Okay, so to find the minimum cost, we want to check our critical points and see what's going on with our function. So we're going to take the derivative of my cost function with respect to W, and that will give us 40 W, and then the derivative of 180 over W is minus 180 over W squared. And in case you're not seeing it, I'll do it up front. If I think of it as 180 times W to the minus 1 for the function, then its derivative, the 180 goes along for the ride, but the derivative I do power roll, so I get minus 1 times a W, and I subtract 1 from the exponent. So you can see that that becomes minus 180 over W squared. Okay, so that's my cost function derivative. Now I'm going to go ahead and do a common denominator. So I'm going to multiply my left term, top and bottom, by W squared. That will give me 40 W cubed minus 180 over W squared. Now I want to set this equal to 0 and or DNE, and I'm going to try to find all my critical points. Well, the bottom, if W equals 0, then the bottom goes to 0, but that also is not a practical box. So that's outside. That's kind of like an edge point, but not a practical box. I don't think the manufacturer is going to go for that one. But we get the 0 case when the top goes to 0. So let's solve that real quick. So we're going to set the top equal to 0, 20W cubed minus 180 equals 0. So if I solve for W cubed, I can do that by adding 180 to both sides and then dividing by 40. Can cancel the zeros because divide both top and bottom by 10. And then W is then the square root, not square root, cube root of 18 over 4. And that, if I plug it into calculator, is about 1.651. Okay, so we want to find out if this is a min or a max. And so what we can do is basically check our critical points and our endpoints. And that's one way to find out if it's a min. Another way is to basically do kind of a sign chart. So I think this time I'm going to do a sign chart. I need to make a little room. And so I'm going to do it here in this little space. Make some space here on the left. Because just because we get a critical point, we have to really show that that value is actually truly a min. All right, let's do a sign chart. And we know we have a critical point at 0. And 0 is really like an endpoint. You can't get W any smaller than 0. But our main critical point is 1.651. So we're going to look at X and see prime of, sorry, it's not X actually, it's W, isn't it? So let's go make that a W, fix that as a W. And then we're going to look at C prime of W. Here we had a little D and E case. And here we had a 0. Okay, so let's see what happens if we plug in something smaller than 1.65 into our expression. Let's plug in, say, 1. So if we plug in 1 for C prime, notice that I will get, if I look at this expression, I will get 40 minus 180. That is definitely negative. Now let's plug in something really big, well, bigger than 1.651. How about 2? So if I do plug in 2, that gives me 80 minus 180 over 4. Let's do a quick calculator just to make sure I do it right. So I get 80 minus 180 divided by 4, and that is a positive. That's still a positive value. Okay, so notice how within our possible ranges for W, that since the derivative is going from negative to positive, we definitely have min. Okay, excellent. So therefore, but we're not done yet because we don't just want the W, we want the actual minimum cost. So we want to take our W value and plug it back in. So our C then at 1.651 is going to equal, and let's go ahead and use this one because it's right there. Okay, so we'll plug in 1.6514 each W, so squared, plus 180 over 1.651. And when we plug that in our calculator, we get that the cost, the cheapest cost for this box is 163.54. So we'll just leave it as dollars and cents. All right, so that is the cost of the least expensive box that can be made according to the recommendations. So that's really great. And by the way, the W was in meters. So this is actually a pretty big box. So it's really pretty much a huge box. Anyway, there it is. Okay, so hopefully that helped. I do love these application problems. Have a wonderful day and see you next time.